Yes, hello everyone on this exceptionally hot day in Vilnius this morning. I want to talk about one of the most ominous dangers of global warming, namely the danger of passing tipping points in the climate system, and in particular my research topic for more than 30 years, the tipping point of the so-called Atlantic overturning circulation. So what is the Atlantic overturning circulation, or meridional overturning circulation as it is called, in short AMOC? Meridional just means in north-south direction. It is a warm surface flow going along the entire length of the whole Atlantic, from the South Atlantic to the very North Atlantic, shown in red here. In the northern Atlantic, the water sinks down to 2,000, 3,000 meters depth, and then it returns as this cold deep current, the North Atlantic deep water, back to the south, shown in blue here. So you have warm waters moving north along the entire length of the Atlantic Ocean, sinking down, giving off its heat first to the atmosphere and returning then back south as a cold current. It works like a central heating system, and it has a massive influence on European climate, and not only European climate. So this is not the same as the Gulf Stream. It's often confused, but this flows along the Gulf Stream path of the North American coast. So in that sense, the Gulf Stream is a part of that larger scale overturning motion of the Atlantic Ocean. This last slide was a little bit simplified. Reality is more complex. Even this diagram is still simplified, but the deep water formation, as we call it, so the sinking down of the water to the depth of the ocean, because it gets very heavy, this water, happens first of all in the subpolar Gyre region, but a second big region is up in the Norwegian Sea. Now, the effect on climate is really large. This is what the world would look like compared to today's climate if you just switch off that AMOC. And you see the scale goes from 20 degrees Celsius colder to 20 degrees warmer. And you see especially the whole northern hemisphere would cool if you shut down the AMOC, and the whole southern hemisphere would warm. And off the Norwegian coast, annual average temperature there would cool by about 20 degrees Celsius. This is not just a theoretical idea, because we know there have been abrupt climate changes in Earth history, most notably during the last ice age, and they are caused by abrupt changes in the AMOC. In this case, this diagram shows the so-called Dansgaard-Oeschger events. They are actually abrupt warming events that happened when this deep water formation flipped from being in just the subpolar Gyre region in this state to going further north into the Nordic seas. And already this had a massive influence on temperatures over Greenland, shown in blue here. This is from a Greenland ice core. These Dansgaard-Oeschger events with the numbers, they are abrupt warming events of the order of 10 degrees within a decade or so, and then lasting for hundreds of years until the system flipped back down again. Likewise, there have been occasions when a lot of meltwater from the ice sheets went into the North Atlantic, iceberg armada slipping down of the ice sheets, so-called Heinrich events, which shut down the AMOC, which then had a massive cooling effect. So these instabilities in the AMOC have repeatedly happened in Earth history, and they had massive climate repercussions. So what is happening now as we are in a phase of extremely rapid global warming, now ongoing about 20 times faster than the end of the last ice age. No similar rapid global warming has been known in the Earth's history. I'm a paleoclimatologist, studied paleoclimate for over 30 years. And this is just the last 2,000 years. We see on the top the carbon dioxide increase, and on the bottom the temperature increase. We're now at about 1.2 degrees. And of course, this is not, we don't think because of this correlation that the CO2 causes the warming. We knew that beforehand. That was already known in the 19th century. The first person who quantified the coming global warming effect due to CO2 increase was the Swedish Nobel laureate Svante Arrhenius in 1896. So what is happening if you look at the map of this warming? That's what it looks like. The observed warming since the 19th century, the entire planet has warmed with one big exception, namely the northern Atlantic, exactly the region where the AMOC delivers its heat. And that has been predicted for a long time by climate models. Here's an example from the last IPCC report. This is now a scenario for the year 2100 for the temperature change, and you see again the whole world warming. This region in the northern Atlantic cooling in the forecast, and that is because the AMOC slows down in these IPCC future scenarios. Now, to study this in more detail, we use these climate models. This is what the sea surface temperature looks like in a global coupled climate model, ocean atmosphere model, the typical type of model being used for future projections. And you see nicely in dark red, that means warm water, the band of the Gulf Stream moving up the North American coast, separating from the coast at Cape Hatteras, that is this little corner here is Cape Hatteras, and then becoming unstable into these meanders. But generally, the heat gets transported further up and is given off to the atmosphere there. And if you use this model and ramp up the CO2 concentration in this model, then you can you get this sea surface temperature change in the model. Now, this has been normalized. That means it has been divided by the global mean sea surface temperature change. All you need to understand about that is that everything that is blue has warmed less than the global mean sea surface temperature or even cooled, and everything that is orange or red has warmed more than the global mean. And now you can see that cold blob in the northern Atlantic in the model simulation, but you can also see a very strong warming of the North American coast there, north of Cape Hatteras, where the Gulf Stream leaves the coast. Now, both these phenomena, both the cold blob and the warming of the American coast, is actually caused by a slowdown of the AMOC in that climate model simulation. And of course, in the climate model, we know this because we have the full information, unlike from the real world, where we don't actually have measurements of the AMOC going back the last 100 years or so. So we don't have this information. I'll come to that. But in the model, we know everything that happens, and also we understand the physics, because when the AMOC slows down, it not only delivers less heat to the northern Atlantic, that explains the cold blob, of course, but it also makes the Gulf Stream shift closer to the shore along the American coast there, which leads to that strong warming up north, and to the south of it you can just recognize a blue bit where it's cool. So the Gulf Stream has shifted a bit north, and that's also a result of the AMOC slowing down. The physics of that has been understood for about 20 years now. Now, this is what the observed sea surface temperature data look like when they are plotted in the same way as the left, the model simulation. And I think you can see the same kind of pattern, only it's very fuzzy because we don't have sea surface temperature measurements since 1817 every year, everywhere. So there's an amount of space and time averaging involved in reconstructing this trend. But I think this fingerprint pattern of an AMOC slowdown, including the cold blob and the warm part at the American coast, is clearly visible. And this pattern corresponds to a slowing of the AMOC by about 15%. We can also look at this with the satellite data since the beginning of sea surface temperature satellite data sets. Now you get it in much higher resolution, of course, because it's satellite. And you see beautifully this fingerprint pattern, you see the cold blob, but now you can also see how there is this warmth along the American coast, and to the south of it there is a bit of blue, so the warm Gulf Stream has shifted indeed closer to the shore. So it's enlarged a little bit. So I'm talking about this warm streak here and this colder one. The whole current has shifted north and it has weakened, which leads to that cold blob. Similarly, the salt content of the ocean has decreased in that cold blob region, which is of course what you expect when the AMOC slows down, because the AMOC brings salty water from the subtropics up into the high latitudes. Subtropics, a net evaporation region, that's why the ocean is salty there. The high latitudes are net precipitation region, that's why the ocean is not so salty there. So we have a decrease in salt content in the cold blob region, and we have this increase in salt content here where the Gulf Stream has moved north. So that entirely fits this pattern as well. And the data actually show that as long as we have the data in the last 120 years, the salinity in this region is now the lowest that has ever been observed. Also, there are studies that directly look at the Florida current, which is a southern part of the Gulf Stream going up the coast of Florida, and that has actually weakened. Another study that came out last year shows robust weakening of the Gulf Stream itself during the past 4 decades. So this is all corroborating evidence for the fact that the AMOC has indeed been weakening in the last decades as a result of global warming. We can use sediment data and other types of paleoclimatic data to look at this phenomenon even further back in time. And we recently published a study a few years ago compiling evidence from other studies from paleoclimatologists that work with these deep sea sediments and so on. The studies are listed there, reconstructing the strength of the AMOC for the last 1,000 years and more, and they all agree. They all show a pretty stable AMOC for the last 1,000 years, but then in the last 100 years or a bit more, you see this very strong decline, and our conclusion in this study was that the AMOC is now weaker than any time in at least a millennium. Now, what consequences does this weakening of the AMOC have for our climate? Just one slide on this, maybe a bit surprising to you. It actually leads to stronger heat waves in summer in Europe. Why is that? A study showed that in 2016. It's because that cold blob likes to have a low pressure area above it, and the low pressure, you know, the wind goes counterclockwise around that low pressure, as shown by the red arrow there. And so we get warm air coming from the southwest into Europe, enhancing the probability of heat waves. And that has been shown again 2 years ago by a study from my department at the Potsdam Institute, showing that Europe indeed is a hotspot of heat waves where they're increasing 4 times faster than on average at similar latitudes. And it's shown in this map here, but also in this probability distribution where this kind of, it's like a Gaussian normal distribution of heat, and it shifts to the right with global warming, of course, towards warmer temperatures. And the blue one shows how typical mid-latitudes on average have shifted the heat wave intensity to the right. And the red one for Europe, it has shifted much further to right. So just showing that indeed heat wave intensity in Europe is increasing much faster than elsewhere in comparable latitudes. Okay, now I promised to talk about a tipping point, so that's our next part. In the first part, we have seen the AMOC is already weakening, and the second question is, what about this tipping point? Now, a tipping point can be explained quite easily. Imagine a ball sitting in this bowl-shaped thing here, and if this person pushes it a little bit, it will roll back to its equilibrium, because that is a stable equilibrium, except if the person pushes that ball beyond that apex point shown by the arrow there. If it goes over that hump, from then on, it will continue its movement without further pushing, just by its own internal dynamics. And that is the definition of a tipping point, also by the Intergovernmental Panel on Climate Change, IPCC. And you see from this simple example, you don't need rocket science for that. It's something very common in physics. You can, if you're a school student wobbling around on your chair, you can do it so far, and from a certain point on, your chair will just fall over. There's another example of a tipping point, or push your coffee cup to the edge of your desk. If you push it too far, yeah, you get the idea. And this is exactly how tipping points in physics generally and also in the climate system happen. The first person who prominently warned about this for global warming was the famous American oceanographer Wally Broecker. And he wrote in the top science journal Nature in 1987 about these unpleasant surprises in the greenhouse. And that is an article exactly about the risk of abrupt ocean circulation change as a result of global warming. And he put it quite drastically. We play Russian roulette with climate, and no one knows what lies in the active chamber of the gun. More modern view of this, now we have a big 500-page report. Last year, 200 scientists from over 90 institutes from 26 countries wrote this massive report and concluded that harmful tipping points in the natural world pose some of the gravest threats faced by humanity. Their triggering will severely damage our planet's life support system and threaten the stability of our societies. That is really what we're talking about here. The IPCC has made similar statements saying that risks associated with large-scale singular events or tipping points, such as ice sheet instability, it's a classic tipping point, ecosystem loss from tropical forests, for example, transition to high risk from moderate to high between 1.5 and 2.5 degrees of global warming. So that is here really giving a range where this is really becoming a high-risk issue. And it is, once we go above the 1.5 degree, this is becoming real high risk. And this is one of the reasons why in the Paris Agreement, all countries committed to efforts of limiting global warming to 1.5 degrees. So for the AMOC, let me quickly explain how this tipping point works. This is from a paper in 1961. Another famous oceanographer from the United States, Henry Stommel, described the problem of the tipping point for the Atlantic overturning circulation based on a very simple model. And the equilibrium states for the AMOC, that's what on the vertical axis, the strength of the AMOC, are shown in the green lines, as they depend on the amount of fresh water going into the North Atlantic. Why fresh water? Because fresh water dilutes the salt content, and less salty water is less dense. The density, especially for the cold waters, depends mainly on the salt content. And so if you add too much fresh water, the surface waters get so light that they can't sink down anymore. And this sinking down motions of heavy water is what drives this whole overturning. And so when you start from an equilibrium, maybe round about here, and you add more fresh water, say from more rainfall with global warming, more ice melt from the Greenland ice sheet, then you move on towards the right here, but you come to this, what is called a bifurcation in the language of physics, where this curve turns back on itself, and there is no more stable state with an AMOC. It has to break down from that point. Why does it look like this? It's very easy to explain. It's a self-sustaining feedback. The water sinks down because it's salty, but it is salty because we have the AMOC bringing salty water from the subtropics. And so if you just have a simple model with two equations, the flow is proportional to the density difference, and the density depends on the flow, you get a quadratic solution. That's what this is. It's a parabola here lying on the side. That's a quadratic solution. And it basically shows why there is this bifurcation point, which is the tipping point, of course. And of course, this is an equilibrium state, the equilibrium states, but with global warming, of course, we are moving away from equilibrium, and we're weakening the AMOC, so we're more on something like this blue trajectory now, where this actually, when it crosses this dashed line, it will cross the tipping point and will die, basically. It will break down. Now you can say, okay, this is a very simple model, two equations, etc. But already in the 1990s, I repeated this, I tried this with a fully fledged three-dimensional ocean circulation model, global model, and there you can't calculate an equilibrium because it takes thousands of years of model simulation to really equilibrate the system, but you can gradually ramp up the amount of fresh water. That's what's done in the orange line there, until you fall off the cliff there. And if you do the same ramping up experiment in Stommel's box model here, you get the black line. If you do it in a fully three-dimensional global ocean circulation, you get the orange line, and you see they're exactly on top of each other. So the very simple box model by Stommel is kind of one-to-one confirmed by fully 3D ocean circulation model. And it has been tried with a number of models now, and you always get this kind of result. So this is really confirmed that this tipping point really exists. Now, the big question, of course, is how far away are we from this tipping point? And this is where there's a big uncertainty. And there are many reasons why models probably underestimate this problem. For example, if you look at what do global warming simulations show up to the present? You know, if you run a global climate model with the CO2 increase and other greenhouse gases, etc., that we have seen up to now, you get this right-hand side picture from the IPCC report. This is what the observations show. So the models, they only predict this slowing of the AMOC for the future, as I showed you in an earlier IPCC diagram, but not yet, but we're already seeing it now. So that's one reason to think the models underestimate this problem.
Delicate balance of salt and fresh water.
We all know that.
Yes, but no one has taken into account how much fresh water has been dumped into the ocean because of melting polar ice. I think we've hit a critical desalinization point.
So I don't know who of you has seen this movie from 2004. It is exactly about this ocean circulation passing this tipping point. And so that's what he calls a critical desalinization point. It's because of the fresh water. And he says in this little clip, no one has taken account of the melting of all the polar ice. And that is still true in modern climate models, because most of them don't fully include the meltwater coming from increasingly rapidly melting Greenland ice sheet. It's just most of these climate models don't have an interactive Greenland ice sheet included yet. And that's another reason why they probably underestimate in the future scenarios the risk of passing that tipping point. Then also the tipping point, of course, depends on a very subtle balance of salinity in the whole Atlantic Ocean in 3D down to the depth, etc. And this is very difficult to get right in the models because it depends on evaporation minus precipitation. You need to really accurately simulate the precipitation, all the clouds, etc. over the Atlantic, where we have very scarce observational data about rainfall amounts for the first place. And also clouds are notoriously very difficult to get right in climate models. And so typically climate models are very biased in the salinity distribution. And here's one study that has corrected that bias. And before they corrected the bias for the future, they get the AMOC weakening, that's the blue curve, but not going over the tipping point. Then they adjusted the salinities in the South Atlantic, actually, to get a more realistic picture, and then they got the orange response to a standard CO2 increase scenario. So that model shows if you improve the salinity distribution in the Atlantic, then the AMOC becomes more unstable and in a regular global warming simulation already passes the tipping point and breaks down. Now, another way to try and find out where the tipping point is comes from nonlinear physics, not at all from climate science, and is the so-called early warning signals or critical slowing down. So it's if you have the ball in that ball-shaped thing again as an analogy, and there is noise, then it will wiggle around the whole time to some extent. Now you change the climate, so you change that background, that black curve. It is still going to wiggle around here, but the side is more flat now, so it will take longer to come back to its equilibrium, and that's what's called critical slowing down. And you can observe the random variability of the system and look for signs of that slowing down or increased autocorrelation. They're all signs of approaching a tipping point. And that has been done in a number of studies, an important one by Niklas Börs from the Potsdam Institute. He looked at 8 different data sets for the AMOC, reconstructed based on temperature patterns, etc., because we don't have direct measurements going back very far. And to cut a long story short, where these dashed trend lines hit the top of the graph here, the 0 line, that's where the tipping point is in this early warning signal analysis. And this is quite scary because, you know, in the 2000s, early 2000s, 3 of them with a salt content, 2 further already suggest that's where the tipping point should be. So it might be actually very close. We could have even already passed it without noticing because nothing drastic happens at that point, except that from now on there will be an unstoppable decline of the AMOC, and we will know that in a few decades whether this is really happening. That was a conclusion from that study. Here's one that used data going back more than 1,000 years, a lot of sediment data from all these points around the northern hemisphere, because you can see that Atlantic variability in the whole temperature data history of the northern hemisphere. And they find at the end here this critical slowing down, and that study concluded that the AMV, which means Atlantic multidecadal variability, but it actually refers to the AMOC, may now be approaching a tipping point after which the Atlantic current system might undergo a critical transition. And there have been more recent studies, there have been newspaper reports like this one from the Washington Post. Here's another one from the New York Times from a couple of years ago. And new studies coming out. Last year, you might have seen the headlines about this Danish study. And quite recently, there was a study from Dutch colleagues from Utrecht, who are, I think, the leading group in this topic now. And actually, on Monday, I go to a workshop for a 3-day workshop on this AMOC tipping point in Utrecht with this group of scientists. Yeah, it's really not looking good. It looks like so far greatly underrated danger. And just to remind you what the consequences would be, this is now for the February temperatures in the model of that Dutch group. When you go over that tipping point in the following 100 years, This dark blue areas now, they cool actually by 40 degrees Celsius over that 100-year time span after the tipping point has crossed. So we're talking about like 4 degrees per decade. It's shocking. I mean, now we've had 1.2 degrees of warming over a 100-year time span, and now if you get several degrees of cooling per decade, this is going to be detrimental. Now, this is only the AMOC change without global warming considered with it, but there are also simulations that look at a 2 times CO2 scenario, so doubling of CO2 in the atmosphere, and the AMOC has collapsed. Then it looks like this. In the top picture is a temperature change in the annual mean, so you have the entire globe got a lot warmer from the 2 times CO2. And except for the North Atlantic region, including Great Britain, Scandinavia, that have cooled massively. And sometimes I get asked by German journalists, oh, well, doesn't that nicely compensate global warming? If the AMOC shuts down, we get the cooling and the effects compensate. Now, you might say where it's white, actually, yeah, in annual mean, they might just about balance. But look at how the temperature gradient across Europe changes there. Of course, the weather, sometimes you get cold air coming from the north, sometimes you get hot air from the south, and this is going to get much, much more variable if you have such an increased temperature gradient. Also remember that winds are driven by these temperature gradients. So this looks like a crazy stormy climate to me with absolutely unprecedented weather extremes all across Europe. But let's go back one here to look at the bottom panel. This is a change in precipitation patterns. And here you see a phenomenon that the tropical rainfall belts have shifted south. So where it's purple now, it's getting a lot drier, and where it's green, it's getting wetter. And that is because the northern hemisphere gets cooler and the southern warmer, and the tropical rainfall belt is where it's warmest, and the air rises and therefore rains down. And in our current climate, the northern hemisphere is 1 or 2 degrees warmer than the southern hemisphere overall because of the AMOC transporting so much heat from the southern hemisphere into the northern hemisphere. So once you turn off the AMOC, both hemispheres will have approximately the same temperature, and the tropical rainfall belts, which are now north of the equator, will move south. And that means the tropical rainfall is not anymore where the rainforests are. That'll be a big problem. And regions that are not used to big, massive tropical rainfall amounts are then getting them. So this will be a massive problem in the tropics as well, not just in Europe. So if you want to read more about this thing, I just published a summary of 30 years of my collected research and wisdom on this topic. Open access, understandable, and fully peer-reviewed. So in this article, you can download it from the journal Oceanography. You can read all about it. My summary conclusion here, the AMOC is weakening. I'm convinced that the evidence is overwhelming for that. We also are certain that it has a tipping point, but the big uncertainty is how close the tipping point is. But recent studies really point to a risk being much larger than we thought, than even I thought until 5 years ago or so. And therefore, we must apply the precautionary principle. This is a disaster we need to avoid at all costs. And that is something that also the IPCC agrees with what the IPCC is saying about global warming in general. There is a rapidly closing window of opportunity to secure a livable and sustainable future for all. We're sure about this. And the choices and actions implemented in this decade will have impacts now and for thousands of years to come. That's because CO2 stays in the atmosphere actually for more than 100,000 years, unless we actively pull it out again, which is hugely expensive. And so what we do this decade decides our climate fate for thousands of years, even without tipping points. Of course, when the AMOC is tipped, that's it, it'll stay off for probably 1,000 years at least. That's why these European elections coming up, of course, are extremely important. It's all about whether the European Green Deal will survive or whether it will be watered down massively. That is really a threat if the majority in the European Parliament is changing after this election. So that's what I wanted to tell you. If you want to read more, I've written a couple of books. And thank you very much for listening. Thanks.